Welcome to our first workshop of the semester. It'll be over substitution reactions. We were going to have others earlier, but yeah, that didn't happen. So let's go ahead and begin. The substitution reactions essentially involve two fundamental things. Actually, I'm going to go ahead and skip to the bottom where you have some open space. But essentially, substitution reactions always involve a nucleophile and a substrate. So let's take a look at what that actually is going to mean. I'm going to draw something here. So your nucleophile is always going to have, we only give you very, very few certainties in chemistry. So when I say always here, appreciate it. But the nucleophile is always going to have a lone pair of electrons on it. Okay. And the reason is because in order to form a bond, you have to have a lone pair of electrons able to be donated or to be able to bind to the substrate or whatever it happens to be. So typically your substrate, which I'll just abbreviate SUB, typically your substrate is attached to a leaving group. And so the mechanism for these types of reactions is either one or the other two things. It's really pretty simple actually. Either you have SN1 or SN2. Now, SN1 stands for substitution by nucleophilic addition, and the 1 means that the rate determining step is unimolecular. Whereas other SN2, substitution by nucleophilic addition, and the rate determining step is bimolecular. So, rate determining step is unimolecular, which means it only involves one molecule. Whereas SN2, rate determining step is bimolecular. Two molecules coming together. Now, SN1, interestingly enough, always happens with in at least 2 steps, a minimum of 2 steps. Sometimes there's other steps needed, but a minimum of 2 steps. And those 2 steps are as follows. First, the leaving group has to leave on its own. And that typically gives you a substrate with a positive charge. And then the leaving group is going to have a more negative charge as a result. Okay, so that's the first step. The second step is nucleophilic attack. And that gives you the nucleophile bonded to the substrate. Now with SN2, what you're going to have instead of these multiple steps, you're going to have it all happen in one step. Just out of curiosity, have you already covered this already?
I did not go yesterday. We probably did. We barely touched on 7 before the test, and she just removed some of it from it.
Okay. Okay. So then, for a nucleophilic addition with SN2 mechanism, what's going to happen is that the nucleophile is going to attack the substrate, and at the exact same time, the leaving group is going to get kicked off. As the nucleophile comes in, leaving group leaves. And this happens via what's known as a backside attack, okay? So it has to attack from the back. And then basically that's going to give you the product here. Now, what do you need for a substitution reaction? I mean, well, you have to have a good leaving group. A leaving group, if a leaving group is not going to leave, you can't have a substitution. Yeah. If the leaving group's not going to leave, you can't have substitution. I used to have a student who would come up with all of these crazy stories about dysfunctional marriages and things like that to describe SN1 and SN2 reactions. And I won't use any of those. But
Man, well, when you have such great terms as backside attack.
You know, the funny thing is, I actually came up with a rap song to distinguish between SN1, SN2, and E1 and E2. E1 and E2 are elimination, and you actually have to distinguish between what's going to happen when, and it can be pretty tricky. And we're tackling this one at a time, but you'll actually get to the point where you have to distinguish between whether or not substitution or elimination is gonna happen. And you know, with the notion of backside attack, you can be not entirely surprised that the rap parody that I did on this is based off of Sir Mix-a-Lot's "Baby Got Back." So shame on me. But anyway, I'll have to share it with you at some time, although I don't know if you really want to hear me say it. But basically, you need a good leaving group and you need a good nucleophile. And there's different conditions that will help you determine whether SN1 or SN2, an SN1 or SN2 reaction will happen. And I'm going to go ahead and actually set up a little flow chart for you to help break it down, because you know how much I love flow charts, and I think you love them too.
Yeah.
So, give me some paint. And I'm going to go ahead and share my paint. First question you have to ask yourself is there a good leaving group? Question mark. And then alternatively, can you make it into a good leaving group? Because you have to either have a good leaving group or you have to be able to turn something into a good leaving group in order for a substitution reaction to occur. So if I use blue for yes, that's fun. If the answer is yes, then we'll ask ourselves another question. If the answer is no, then there's no reaction. So no reaction if there's no leaving group. So the presence of a good leaving group or the ability to make it into a good leaving group is the most important thing. So no or yes. And then if the answer is yes, then the question is you have to ask yourself is where is the leaving group? Where is the leaving group? And there's three possible answers here. You can have a leaving group that is primary, secondary, or tertiary. Now, just as a quick double check reference, do you know what I mean by a leaving group that's primary, secondary, or tertiary?
Where they're connected to a carbon?
Yes, specifically how many carbons the carbon that's attached to the leaving group is connected to. So let's see, I'm going to color code this actually. Let's call, oh shoot, I didn't mean that for that to turn to blue. Oh well, I'm going to color code this. We'll do red. Red will be primary. Primary. And then we'll have orange be secondary, or actually this will be red, okay. And then we'll do orange will be secondary. And then blue will be tertiary, or purple. Okay. So if you have a good leaving group and it's a primary, it's in the primary position, which means, just as a quick summary, and you'll also see primary sometimes written like this. Okay. This just means that the carbon that's connected to the leaving group is connected to 2 hydrogens and another carbon. Now that carbon could be connected to anything it wants to be, like anything it happens to be, it doesn't matter. But the key thing here, the thing you want to pay the most attention to is this guy in the middle. The carbon connected to the leaving group is only connected to 1 carbon. And then for secondary, as you can probably imagine, the carbon connected to the leaving group is connected to 2 carbons. Two carbons and 1 hydrogen. And those carbons could be connected to other things as well, but it doesn't matter. It's really the carbon that's connected to the leaving group that we care how many carbons it's connected to. Okay. And then last but not least, we have tertiary. And of course, at this point, you probably already know what I'm going to say. The carbon connected to the leaving group is connected to how many carbons?
3.
3. You read my mind. Okay. So the question that we have to ask ourselves after this is, do we have a good nucleophile? Okay. So, actually, let me, yeah, I'll write it in black. Why not? Do we have a good nucleophile? And it's And actually, it's the same question we asked for the other two as well. And we'll talk about in a second what makes a leaving group a good leaving group and what makes a nucleophile a good nucleophile. Because that's really important, actually, as you might expect. Now, just to sidetrack, a good leaving group is going to be anything that is a weak base. So a really weak base or neutral ion is going to be the best, or like when I say neutral, I mean neutral in terms of pH. Like spectator ion, think spectator ion. So like if you have bromine or chlorine or iodine, those are really good leaving groups because they're spectator ions. They don't really react with anything. They're things that, they're conjugates of strong acids, basically. So good nucleophiles, or good leaving groups rather, are weak bases, and the weaker the better. The stronger a base it is, the worse of a nucleophile it is. The weaker the base it is, the better the nucleophile. So, bromine, chlorine, iodine, good leaving groups. Also, water is a good leaving group. There's something called p-toluene sulfonomethane, or p-toluene sulfonic acid. Its conjugate base is a good leaving group. You'll see some of these things as we go through the different examples. OH, as you might imagine, is not a good leaving group because OH, or hydroxide, is a strong base. Carbons are terrible leaving groups. Hydrogens are terrible leaving groups because keep in mind that when it leaves, it has to take its electrons with it. So you need something that can stably hold a negative charge that's not going to be reactive with a negative charge on it. And that's why we're looking for something that's a very weak base as a good leaving group. All right, so back to our nucleophiles. Do we have a good nucleophile? Now, in the case of a primary leaving group, we have a good leaving group and it's primary, and we have a good nucleophile, then this is going to be SN2 only. SN2 only. However, if you do not have a good leaving group, if you don't have a good leaving group, you're not going to have a reaction. No reaction. Actually, I'm going to change that color. See, and the reason is because in an without a good nucleophile to kick out the leaving group, the reaction simply doesn't happen. I'll give you an example. Let's say, for example, you had chlorine here, and you have, your hydrogen here, and you have, say, a CH2, and then you have a CH3 here. All right. In a case like this, the nucleophile has to come in and attack from behind. It has to kick out the leaving group. For an SN1 reaction to occur, the leaving group would have to leave by itself. It turns out that only good nucleophiles, as you might expect, only good nucleophiles have the strength to kick out the leaving group. Only good nucleophiles have enough kick to them that they're going to hit that carbon hard enough to push out the chlorine. Otherwise, it'll just be very, very feeble. It's like if you were holding on to something and a toddler tried to knock something out of your hands and you were holding on to it really tight, it's not going to work. But if somebody really strong tried to knock it out of your hands, then it might, probably work. So you need a weak nucleophile is just not going to be able to kick it out. It's just not going to be able to kick it out. And the reason, you might be like, well, can't the chlorine leave on its own? Well, the problem with that is that simply is not going to happen, because if it left on its own, you would get this, a carbocation. And carbocations are very unstable. They're unstable to begin with, a positively charged carbon. They're very unstable to begin with, but they get more and more unstable depending upon how many hydrogens are attached to it. So if you have more and more carbons, in other words, if you have a primary carbocation, it's going to be extremely unstable. If you have a secondary carbocation, it has a couple other carbons bonded to it, and those carbons have more electrons that they could potentially donate or share through a process called induction. You've heard of resonance, right? What's resonance?
The move of your shared electrons.
It's the movement of electrons across pi bonds, right? And pi bonds are those the bonds formed from p orbitals, the double bonds, right? So electrons can move pretty freely on the pi bonds when you have conjugated systems. But you can actually even have electrons move through sigma bonds. It's just not as effective. And the movement of electrons through sigma bonds is called induction. And so a primary carbocation, there's simply not enough electrons around it. It's only bonded to one other carbon. And so only that carbon, the hydrogen just doesn't have enough electron density to donate. And you only have one carbon that can help contribute to that stability of that carbocation. And so primary carbocation is really, really unstable. Secondary carbocations, they're still pretty unstable, but they're stable enough that if you didn't have a good nucleophile, but you had a really good leaving group, a very small amount of the leaving group would leave every now and then. So this is still very unstable, but because you have two carbons that can contribute electrons to that positive charge through the sigma bond, through that single bond, it stabilizes that secondary carbocation. And a tertiary carbocation, while still unstable, is much more stable than anything else. A tertiary carbocation has 3 carbons around it contributing. Tertiary carbocation has 3 carbons around it contributing to its stability. They're all donating some electron density to help offset that positive charge. So, in short, tertiary is better than secondary, which is better than primary. So primary carbocations, they simply do not form. I'll actually emphasize that with big red letters. Doesn't form. Okay. So primary carbocations don't form. Hence, you get no reaction. No reaction if there's not a good nucleophile. And you have a leaving group on a primary substrate. Now, if the leaving group is on a secondary carbon in the substrate, and do you have a good nucleophile? Well, then, if the answer is no, what do you think would happen? Will there be a reaction? What do you think?
I mean, you have another carbon in there, so you have 3 more hydrogen that you can resonate along.
Well, it's not resonating along the hydrogens. It's actually the carbons that will help to share electron density. I'm trying to find where my little thing is. So the carbons can share a little bit of electron density with this and make it more stable. But I think your idea is in the right place. In this case, only one would be able to do so. And tertiary, you'd have 3 carbons that can share a little bit of electron density across that single bond via induction. But yeah, even if you don't have a good nucleophile, if you have a bad nucleophile, the leaving group could still leave on its own. And if the leaving group leaves on its own, a bad nucleophile is still an opportunist. It'll come in and it will form a product. It'll attach itself to the carbocation. So you will get something. What you'll get is an SN1 reaction. So this would be SN1 only. If you don't have a good nucleophile, you're going to get SN1 only. You're not going to get any SN2. SN2 means you have to have strength to kick it out. Now, if you do have a good nucleophile, will you have SN1 or SN2? You have a strong nucleophile.
SN2?
SN2, yeah. SN2 only. Yep, because the strong nucleophile is not going to wait. It's not going to wait for the leaving group to leave. It's going to come in there and kick it right out. Now, let's look at our last one. Tertiary. Whoops. If you do not have a good nucleophile, will this react? If there's no good nucleophile, will this react? What do you think?
Yes, because you're sharing another bond with that carbon.
Yeah, because you have additional carbons that can stabilize that carbocation. So yeah, this is most likely gonna be an SN1 type reaction. It's gonna be an SN1 reaction. But it'll only be an SN1 because you don't have a strong nucleophile to kick anything out. Now, what about if you have what if you have a good nucleophile with a tertiary leaving group? What will you get?
I don't know.
The truth is, you're going to get only SN1. And you might ask, well, why? It's strong. Shouldn't it kick out the leaving group? The problem with a tertiary molecule like this is that if the leaving group's attached there, there's no space, there's no easy way for the nucleophile to come in and attack from the back. The back is all blocked off. So you can't get nucleophilic attack, or you can't get a backside attack on a tertiary carbocation or a tertiary substrate with a substrate with a tertiary leaving group. It's too blocked. It's too sterically hindered would be the word. The nucleophile just can't get in there. So that's going to actually cause this to be an SN1, no matter what. Whether it's a good nucleophile or a bad nucleophile, tertiary leaving group always means SN1. Primary leaving group always means SN2. The only way you have SN1 or SN2 that you have to consider is if you have a secondary leaving group. Now, in truth, this is actually a little bit more tricky because I said SN2 only. That's not entirely true. There are other factors that affect this. So I would actually probably have to change this to SN2 would be the major product. SN1 could potentially be a minor product. And that has to do with a number of different factors. One, even if this is not sterically hindered, or even if it's not only secondary, where the leaving group is attached, you could have a secondary molecule, something like this. I'll show you an example. You could have a secondary molecule like this. So let's say you have a CH, and you have a good leaving group, it's a bromine. But on this side, let's say you have a tert-butyl group. And on this side, you have a tert-butyl group. Does such a molecule exist? You betcha. Now, even though this is technically speaking a secondary leaving group, it's not going to be easy for a nucleophile to come in here, even if it's a good nucleophile. It's not going to be easy for a nucleophile to come in here and kick that out, to kick the bromine out, because all these other groups, all these other CH3s all over the place are really going to block this out, especially if some of these are actually even longer, if these are more extended. Say, for example, you had another carbon coming out here, you know? So it's entirely possible that you could have a situation where SN1 is really your major product, not the SN2. So there's a little bit of flux in the secondary situation. You have to consider whether or not it's sterically hindered or not sterically hindered. Another factor to consider is solvent effects. So I'll mention that briefly here. So there are two types of solvents that you can use for these types of reactions. One is a polar protic. And a polar protic solvent is basically like water, H2O, or alcohol. Essentially anything that can hydrogen bond. Anything that hydrogen bonds, it would be a polar protic solvent, okay? A polar protic solvent is actually going to favor it's going to favor SN1. It's going to favor carbocation formation because the polar protic solvent stabilizes ions, including carbocations. So favors carbocation formation, which means it favors SN1, favors the SN1 mechanism. Ah. Yeah. So solvent effects. Polar protic solvents favor the carbocation formation, which means it favors SN1 mechanism. However, the other type of solvent that you can have for these types of reactions is a polar aprotic solvent. And a polar aprotic solvent would be, anything that does not hydrogen bond. So no NH, FH, or OH bonds. And so that guy that would end up favoring SN2 reactions. And the reason that this is the case is because it prevents the nucleophile from being bound up by solvent molecules. So, do you know what I mean when I talk about solvation? When something is solvated?
No.
Okay. So let's say you have a nucleophile. Let's say your nucleophile is, I don't know. Let's make it an SH. SH minus, okay? When you have something like this, remember most of our nucleophiles are going to tend to be negatively charged. Most of our good nucleophiles are going to tend to be negatively charged because, and at the very least, they're going to have a free pair of electrons to donate. Well, what do we know about, water? Water is a very polar molecule. So if I have hydrogens that have very high partial positives, here we go. Partial positives. And you have this SH with a negative charge, these water molecules are going to swarm this thing. They're going to kind of cover it all up because the hydrogens are going to be so attracted to that negative charge. Because the hydrogens are positive, that positive is going to be very attracted to the negative. And so you're going to get this, what would be a very good nucleophile. It still is a good nucleophile, but it's limited in its ability to react because it's solvated. It's wrapped up in solvent. It's solvated by water molecules. Does that make sense?
Yeah, thanks.
No problem. Whereas a polar aprotic solvent, it doesn't have a strong partial positive or a strong partial negative. It still has a partial positive and partial negative, but it's not going to wrap itself around like crazy, like the water or alcohol and other hydrogen bonding molecules will do. So that's definitely that's one of the reasons why polar protic, it's really going to favor SN1 and kind of disfavor SN2. That's not to say it can't happen in a polar protic solvent, but it just makes it a lot harder and a lot slower. A polar aprotic solvent, once again, it's going to favor SN2 and it's going to disfavor SN1. You usually won't see an SN1 reaction carried out in a polar aprotic solvent. So let's go ahead and jump to some of those questions, those practice questions that I was showing you before. Any questions over any of this that I've gone over so far?
I don't think so.
Okay, cool. So carbocation strength. Our little flow chart here, keep it in mind. It's going to get more complicated, but we're not going to worry about that quite yet. We have other factors to consider. But for now, this is what we want to focus on. All right, let's get to our questions. So I'm going to skip the naming thing. We don't really need to know that. Well, you do need to know it, but you should already know how to know it. Okay, so it says, for each of the following reactions, assume a concerted process is taking place and draw the mechanism. What does it mean for there to be a concerted process?
Everything's happening at once, so it's your SN2.
Yeah. Yeah, so when it says a concerted process, concerted is synonymous with SN2. So, question. You have this NaOMe. Now, it doesn't tell you what the solvent is, so you can't rely on solvent effects. But what can you presume to think about the charge of this oxygen? Sodium's not a very electronegative element, right? What charge does sodium tend to have?
It's electronegative. So it has a positive charge.
It's a positive charge. It's actually not electronegative. And so if sodium has a positive charge, that means this oxygen probably has a
negative
charge. So this is actually a good nucleophile. It's also a very strong base. Strong bases do tend to be good nucleophiles. Although as you'll see later, they can also do other things. So, and let's look at this particular carbon that's attached to the iodine leaving group. Iodine, of course, is a good leaving group because if you give it a negative charge, iodine, well, that's a spectator ion, right? That's a conjugate of a strong acid, HI. Mm-hmm. So, is it a primary, secondary, or tertiary?
Primary.
Primary. So in this case, even if it didn't tell you it was SN2, because this is a primary leaving group and you have a strong nucleophile, you would know that this is SN2. So what's going to happen is this oxygen is going to donate electrons to this carbon. It's going to come in from behind, and that's going to kick the iodine out. And so this OMe here is in fact this O and this methyl group here. Now, another thing I should mention about the SN2 mechanism is that if you have chiral molecules, y'all remember what chiral molecules are, right?
Yeah.
If you have chiral molecules, SN2 reaction will actually cause the configuration to flip. So if it was previously S, it'll turn to R. Previously R, it'll turn to S. It'll flip the configuration. Okay, so that's your mechanism. It's actually pretty straightforward. Now it's for the second one. It says for each of the following reactions, assume a stepwise process is taking place. Stepwise means in all likelihood SN1. So this is going to be SN1. And the first step is going to be what? What's the first step of an SN1 reaction?
You have to have something leave.
You have to have something leave. In this case, what's going to leave?
Probably that iodine again.
Yep. So first things first, iodine leaves these electrons, it takes its electrons with it. And that's going to give you this. Yeah. 1, 2, 3, 4, and a positive charge here. Because with that iodine gone, these carbon groups are going to move as far away from each other as possible. You had 1, 2, 3, 4, 5 carbons before. You have 1, 2, 3, 4, 5 carbons after. So then, what's going to happen at this point then?
Your sodium and chlorine need to break apart.
Do they need to break apart, or are they already apart?
Are they?
So, I mean, generally speaking, remember sodium is a spectator ion, right? So
Right.
these are probably already going to be broken apart. Sodium's not going to hang on here. These are going to be pretty much be broken apart. Although if it is a polar aprotic solvent, yeah, I mean, it's not going to be as separated as if it was a polar protic solvent, but they're going to be broken apart. Okay. So this chlorine is really just going to, these are actually just two ions that are close to each other with a positive and a negative charge. The chlorine really has 4 lone pairs around it, and sodium doesn't really have any lone pairs that can call its own. But this is going to come and attack the positive charge. And there is no backside attack because for a carbocation, what is the molecular geometry of a carbocation?
Tetrahedral?
No, not tetrahedral. You only have 3 electron domains.
Planar?
It's trigonal planar.
Oh.
And so and that's why there's no backside attack. There's no reason to go backside attack. It's top or bottom. And
okay.
And this is why in an SN1 mechanism, your products, if they were chiral before, so if this was a chiral carbon right here,
right?
So if it was chiral before, you'd actually get a racemic mixture. In other words, it's just as
half would be S, half would be R.
Yeah, half would be S, half would be R. It'd be just as equally likely to go top or bottom,
okay.
And it wouldn't matter which. In this case, it doesn't matter because this is not stereocenter to begin with, but it will start mattering later on, as you'll see. All right, cool. So that's the 2-step mechanism. First, leaving group leaves, then the other one comes in. So now this is draw the product for the file of each of the following SN2 reactions. It says S2-chloropentane. So if I look at this, S2-chloropentane, if I was to draw this initially, pentane's 5 carbons, right?
Yeah.
And so 2-chloropentane. So first I'm going to go ahead and just draw this. Okay, well, here's chloro. I asked myself, if I was to label this as is, assuming that, let's say if I assume that the chlorine, this is what I usually do. I usually assume the chlorine is a wedge, okay?
Okay.
And then see what it would be. So in this case, chlorine is the highest priority group, number 2 priority group, number 3 priority group, right?
Right.
Do you both understand where I got those numbers? Why I said chlorine is highest priority and this is second highest priority?
Yeah, the size of them.
Yeah, so essentially, you look at the first atom it's connected to, and then you go to the next atom after that, and the next atom after that. So a C with another C is better than a C with 3 H's. So this looks like it would be R, but I need an S. So I'm actually going to get rid of that. And instead of making it a wedge, I am going to make it a dash. So this is my S2 chloropentane. Now, for NaSH, this is going to come in on the opposite side and kick this out, pop it out. So I'll actually draw the transition state. So if you're looking at this from the perspective of a tetrahedral molecule, okay? So let's see, you have a tetrahedral molecule, and here's your chlorine. It's out like this, okay? It's starting to leave because the nucleophile, the SH, is coming in. Whoops. So this is starting to form that bond, and that bond is starting to break on chlorine. And here's your carbon in the middle, okay? So this is coming in, and this is going out. This is leaving. And on the top here, you have, let's see. I'm trying to think about this for a second. Oh my goodness. Okay. If I rotated that down. Yeah. Okay. Okay. So then you'd have this methyl group up on top in a wedge, and then in a dash, you have this propyl group. And then you have a hydrogen down here. Basically, as this SH is coming in and attacking this carbon, the chlorine is being kicked out. And that causes this, because these three groups were initially bent this way. They were initially bent this way with the chlorine coming out the other way. Okay? However, the problem is when the SH comes in and pops the chlorine out, it actually causes this to flip around. It's kind of like, did you ever watch Mary Poppins as a kid?
No.
Well, then this may not make a lot of sense to you, but in Mary Poppins, there's this one scene where there's high wind and all the umbrellas flip over. So the umbrella is initially facing this way, but then what happens is all the umbrellas flip over to the other side. So this is going to flip over here, this is going to flip over here. And so instead of being angled like this, it ends up being angled like this. Does that make sense?
Yeah.
So that's why you get the inversion of configuration. So the S comes in and kicks all the groups out to the other side. And that ends up giving you an inversion of configuration. Now, you don't usually have to draw the transition state unless your professor is kind of evil. But, no, I'm just kidding. What you can do simply is actually flip the orientation. If it was a dash before, just keep it the same way, put the new group on it and make it a wedge. And that's the easiest way to deal with it. So your product would look kind of like this. 1, 2, 3, 4, 5. Wedge, SH. Cool?
Cool.
Awesome. Now, in this case, it said what product would you expect in each of the following SN1 reactions? In the case of A, obviously, you know, the leaving group leaves, and then the chlorine comes in. But one thing you have to watch for with every SN1 reaction is that, remember how I said that carbocations are more stable if they're tertiary? You have to check and see if the carbocation is capable of moving to a more stable position. In other words, if you have a secondary carbocation, is there a tertiary position it can switch to? If it can, it'll undergo what's either known as a methyl shift or a hydride shift, and that will cause the carbocation to go from a secondary to a tertiary position. In this case, it's a tertiary carbocation, so the only thing that's going to happen here is that the chlorine is going to add right where the iodine left off. Now, it could add on top or bottom, but it doesn't matter because this is not a chirality center. What about for part B? What do you think about that one? How many products would you get?
2, because your bromine will end up being an independent product.
Well, no, what I meant, how many possible organic products will you get?
Just 1.
Actually, you get 2. Do you know why?
No.
Look at this carbon here. Is that a chiral carbon?
Yeah.
So if that's a chiral position, when the bromine leaves and the SH adds, it will be a chiral position. But since this is SN1 and the bromine leaves on its own, that means the intermediate is a carbocation.
Okay.
So where is the SH going to attack? Top or bottom or both?
Both, I guess.
Both. It's equally probable that it will attack from both, from either side. And that will give you 2 different stereochemical products. You can,
okay.
Yeah, so you can get, whereas this particular reactant was only 1, 2, 3. Looks like S, but it's actually R. Yeah. Although you only have an R reactant, because of the SN1 mechanism, you will get actually both products, both the R and the S. You get the SH on the back, and you'll also get the one with the SH on the front. Ah, what is that ugliness? I cannot draw today, apparently. More challenging than you might expect drawing on a computer. There you go. So yeah, you'll get both of those stereochemical products, both the R product and the S product in a racemic mixture. And a lot of times you'll just see one of them, a lot of times you'll just see one of them drawn, but then it'll say plus En, and that just means plus the enantiomer. Cool. Now, and this problem talks about whether or not you're going to see carbocation rearrangement. Now, for each of the following substrates, it says determine whether an SN1 process is likely to involve a carbocation rearrangement or not.
So that'll have to do with what degree your cation or your carbon is, right?
Yeah, what degree your carbocation will initially be. In this case, iodine's the leaving group, right?
Yes.
So your carbocation would be
tertiary.
Tertiary. Will that undergo rearrangement?
No.
No. That's like buying a TV for $200 and then taking it back to the store and buying it somewhere else for $500. The same TV. That's dumb. Why would you do that? Nobody does that.
Right.
Whereas here you have OH as the leaving. Oh, you might be like, well, OH is not a good leaving group. That's not going to react. Well, the truth is, you're right. But usually with something like this is going to be a reaction. Alcohols tend to react with strong acids. What happens is the first step is kind of a pre-step to the mechanism. The first step is that you get protonation of the alcohol by the strong acid.
Mm-hmm.
And that effectively gives you sorry.
Mm-hmm.
It gives you this. This will get protonated and you'll have a positive charge on this. And OH2, what do you know? That's water. Water is a very weak base. So that's a good leaving group. That could leave on its own. Now that gives you what type of carbocation?
That is a secondary carbocation.
Secondary. So then what you do is you look at the positions that are alpha to that position. So that would be like this one and this one. So what type of carbon is this one down here?
First degree, primary.
Actually, it's not primary. See this carbon here it's connected to one other, it's connected to two carbons, this one and this one. So this is actually a secondary carbocation. Did that make sense?
Yeah.
What about the carbon up here?
Tertiary.
It's tertiary. It's attached to these three carbons up here. So this is tertiary. So will this carbon rearrange? Will carbocation rearrange?
It's possible.
It is possible. And actually, I lied. This is not even a tertiary carbocation. This is not even a tertiary carbon. This is actually a special type of carbon that is called a quaternary carbon because it's actually attached to four carbons, so three up here and one down here. So this is a quaternary carbon. So yeah, rearrangement will happen here. And what happens is since this carbon, the quaternary carbon, has no hydrogens, it wants to move the smallest group possible. So if it could move a hydrogen, it would, but it doesn't have any hydrogens. So it's going to have to move an entire methyl group. So you get what's known as a methyl shift. And so a methyl shift is a movement of the entire methyl group to the new position after this goes away. So this goes away first, it leaves first, and because the leaving group has to leave before a carbocation is formed. Once it's formed, then it can shift. So the leaving group leaves, carbocation shift, the methyl shift, and you get the new carbocation would be here and you'd have this like that.
Right.
And so you now have a tertiary carbocation, and the new group can add there. It's kind of an awful looking molecule, but yeah.
Yeah.
Now, in the case of, if you, let's say you only had secondary, let's say you only had secondary, let's say there weren't these other guys up here, this is actually a primary carbon, would it shift from a secondary position to a secondary position? Could it shift from a secondary to a secondary?
Why would it want to?
That is a good question. Why would it want to?
Is there a secondary position that's more stable?
Well, I mean, that's actually a very good question. Is there a secondary position that's more stable? The answer is yes, but generally speaking, going from a secondary position to a secondary position, just not going to happen, because as you might imagine, doing a shift, a hydride shift or a methyl shift, takes energy. Just
Right.
like taking that $200 TV back to the store takes energy. Like, you already had it set up in your living room. Like, why would you go to the store and exchange it for the same TV for $200 when you paid $200 to begin with, right?
Right.
So secondary carbocations don't usually reshift to another secondary position.
Okay.
It's just not worth it. When it goes from a secondary to a tertiary, that's like taking that $200 TV back and getting it for $50.
Right.
You know, that's worth it. I mean, you'll spend a little extra time and energy doing it, but it's worth it in the long run. All right. Now we look at this last one. What do you think about this one? Will C undergo a carbocation shift? What do you think?
So it's on a secondary molecule.
A secondary carbon, yep.
Secondary carbon. So it could, if its leaving group is motivated.
Yeah. So this would have to be activated. You'd have to turn it into water by reacting with acid. But yes, then it could leave. But yes, so if, let's say this leaves and you have a carbocation here, will that rearrange, and to what position?
I don't think it'll rearrange. I think you get left with a charge.
So,
Because why would you take?
The carbocation will stay here, you mean?
Yeah.
Actually, it does rearrange. There is a hydrogen that's not shown here, right?
Right.
And this carbon is what?
Secondary?
Not secondary.
No, it's tertiary because it's connected to the carbocation itself. Okay.
Yep. There you go. So it's tertiary. So that means this hydrogen is going to move down here. And then you're going to get positive charge up here. And that. You'll get a tertiary carbocation if you have a hydride shift.
Okay.
Very cool. So that's the trickiest part of these substitution problems. And SN2, you will not have rearrangement. You don't have to worry about rearrangement for SN2 because there's no carbocation. But with an SN1 process, you have to watch out for those carbocation rearrangements.
Okay.
Always check and see if there's a rearrangement that's going to occur.
Okay.
So now it says draw the mechanism for each of the following SN1 processes. So in the case of the first one, what's going to happen first? Going back to the flow chart, the first question we ask is, do we have a good leaving group? Yes or no?
I mean, if that bromine counts.
No, it doesn't. That's our nucleophile. Do we have a good leaving group, though?
Yeah, it's okay.
No, it's really not okay. It's actually kind of terrible. Sorry. Yeah, no, OH is a terrible leaving group. But then there's also that sub question we have to ask ourselves: can we make it a good leaving group?
Yes, if you have water.
Yeah, if we can turn it into water. Now, the only way you're going to turn an alcohol into an alkylonium, in other words, turn that OH into an OH2, is if you have a pretty decently strong acid. Do we have a strong acid?
Yes.
Yes, we do. So you have this HBr. So we're going to have the lone pair of the oxygen, grab that hydrogen because that hydrogen is very acidic. And that's going to give you bromine, a bromine ion, and it's going to give you a so this first step is going to be the protonation of the alcohol. Protonation of the alcohol. Now, what's the next step?
You have to break that bond between water and your other molecule.
Yeah, so you get the leaving of the leaving group. So protonation of the alcohol, the leaving of the leaving group leaves. Now we have our carbocation. So we have an electron deficient carbon here, our carbocation. So then what's our next step after that? What do you think?
Why do we want to take an OH group back?
Well, the thing is, there is no OH group to take back. Now, you actually are correct in a sense. You are correct that I kind of deceived you in that this reaction actually is reversible here.
Right.
The adding H3O plus to that water, that it may give that H plus back if there's not necessarily not to bromine, of course, because bromine's HBr is a stronger acid than a protonated alcohol, but it could give it back to water. It could give it back to water.
Okay.
So this is an equilibrium.
Okay.
Furthermore, water could come and attach itself to that carbocation. So this is in fact reversible.
Okay.
However, the water leaves. Now the next, I mean, there's also that, of course, that water that left, and we still have that bromine from up above.
Mm-hmm.
So at this point, what's going to happen?
I don't know.
Well, bromine happens to be negative, and this happens to be positive.
Right.
There's an attraction. So yeah, nucleophilic attack.
Okay.
And it binds there. Now, the funny thing is here, this is actually a mistake.
Oh, so that's why I was asking. I didn't get that we were going to end up allowing bromine to come back. Okay.
Yeah, that's supposed to be a bromine there. My apologies. That's a total mistake. I have to go fix that. But yeah, So my apologies.
Okay.
I now understand your confusion. All right. So yeah, the bromine's gonna come and add to the carbocation, and that's gonna give you this. Now it's not a stereochemical center, so you don't get multiple products. You just get that one product.
Okay.
So, now the interesting thing about this is that once this happens, this molecule is pretty non-polar.
Okay.
So as you can imagine, the acid that this is reacting with is polar. And this is undergoing an SN1 process, so you're probably in a polar protic solvent like water.
Okay.
So the water is very polar, but your product here is non-polar. So once this is formed here, yeah, it's not really going to go back because it's going to be separated. It's going to separate itself. It's going to either sink to the bottom or it's going to rise to the top, depending upon its density. And
Right.
usually the organic layer is less dense, so it'll tend to float on top. So if you were to do this reaction in the lab, you would notice some sort of an oily looking substance kind of sitting on top.
It just wouldn't be miscible.
Did you just do one like that?
Oh, I'm certain we did. I don't know if it was just, but
yeah. So yeah, and so this next SN1 process, you can see pretty clearly here what's going to happen is what?
Oh, same sort of process.
Same sort of process. So yeah, the first thing is this going to get protonated by the H and the HBr. Then you're going to have this group leave. But then you're going to get a carbocation here. That's going to be interesting. Because what's going to happen then?
You have a shift?
Yeah. What kind of shift?
A methyl one?
A methyl one?
It's either that one or a hydride one.
Which one is? I like how you add the Y to the end. A hydride one. No. Hydride shift or methyl shift? That's a good question. Which one do you think is more preferred? Hydride or methyl?
I don't know how to think about that. Do you think about it based on what degree the thing is coming from?
It's easier to move a smaller group.
Okay, so you don't want to move an entire methyl group if you can do a hydride shift instead.
Exactly.
Okay.
So this hydride, this hydrogen is going to move over here, and that's actually going to turn that from a wedge CH3 to a flat pancake CH3.
That's really, that's a lot to think about.
It is a lot to think about.
So
You seem pretty salty about it too.
I just.
So yeah, so now you have the hydrogen that shifted over. That's still here. There are actually two hydrogens, so we don't really care about them, but there's two hydrogens on here. And then this is the carbocation, but the carbocation is automatically going to turn it into sp2, which is a trigonal planar formation. And that means that the bromine, when it comes, it can either attack from top or bottom. But at this point, because of the fact that we move some stuff around, is that carbon in the middle still a stereocenter? That carbon. What do you think?
Yes.
Actually, no.
Why?
It has a line of symmetry now.
Oh,
this side.
It does.
Yeah. This side is the same
Because
as
it
this.
doesn't have that hydrogen. It just got rid of that hydrogen. Oh my god.
Well, the hydrogen moved over. See.
Yes.
Technically speaking, you do have the hydrogen here, but the problem is you have two hydrogens here as well.
Stupid.
I'm sorry. I'm not laughing at your misery. It's just kind of funny. You're kind of crabby about it.
You think you're getting something, and then it just complicates, and you're like, oh, that's right. Let me just go right back to the drawing board, grab the molecule thought handbook. Confidence is not for chemistry.
You're going to get it, though. You're going to get it. You're going to get more and more confident once you realize what to look for. I mean, you're already on a really good path, so don't sweat it. You're in a good shape. Okay. So this has a line of symmetry. So this is no longer a chiral center, which means the bromine can add to it, but it's no longer connected to 3 different groups when the bromine adds, and it's just going to be achiral.
Okay.
And so the bromine then comes and oh, I'm getting echoey. So the bromine is just going to come and add with its negative charge and its extra electrons. Show off yourself. It'll pop itself on there. And whether it pops on top or bottom, it's going to be the same thing.
Okay. It's bonding to the chiral carbon. It's not bonding to the methyl group. Wait.
There's no chiral carbon.
Right, okay. So it's jumping onto that carbon in question. But that CH3, oh, I think it's just the way that we drew it. It's not 2 carbons.
Yeah, it's just 1 carbon, 1 BR.
Yeah, okay. Cool.
Now, in these cases, you have an example of a really good nucleophile in bromine. Bromine's actually a good nucleophile. It's one of the few, like the halogens, they're good nucleophiles, but they're also good leaving groups. So they're one of these kind of weird combinations of both. But generally speaking, good nucleophiles are not necessarily good leaving groups. Good nucleophiles, and that's actually one more thing I wanted to mention. For something to be a good nucleophile, let me go ahead and write that down. For something to be a good nucleophile, it has to be, well, one, it has to have a lone pair. That it is willing to donate. And negatively charged, the more negative the charge, the better the chance it's a good nucleophile.
Okay.
Neutral. Similar nucleophile. So, in other words, an OH minus is going to be better than an H2O, right?
Okay.
Or an NH2 minus is going to be better than an NH3.
Okay.
So, if it has a negative charge, it's going to be a better nucleophile generally in a similar type of molecule. Step 2, the other important thing about a good nucleophile is that you want it to be polarizable. So think of having a lot of electrons. More equals better. So iodine is going to be a better nucleophile than bromine because iodine's a bigger atom, and it's going to be I minus is better than Br minus because it's a bigger atom and has more electrons, and therefore it's going to be more polarizable. And the same thing is true with like SH versus OH. So SH is actually a weaker base than OH. But because SH is more polarizable, SH is a better nucleophile.
Okay.
And another kind of a last thing, a tertiary thing, is that stronger bases make better nucleophiles.
Okay.
But once again, like I said, this is kind of a secondary consideration, because first, it has to have a lone pair that's willing to donate. Negative is better than neutral. Next, polarizable. The more electrons, the bigger the group, the better the nucleophile. And then if the sizes are similar, stronger bases tend to make better nucleophiles than weaker bases.
Okay.
For example, NH3 is a better nucleophile than water.
Okay.
They're similar size, but nitrogen's less electronegative, so it's more willing to give up its electrons because it's a stronger base than water.
Okay. Mm-hmm. Cool. All right.
That's a terrible. Yeah. I kind of feel like that reaction wouldn't happen. 724. I'm looking at 724, and I don't like it. For that reaction to happen, you'd have to add like a bunch of heat. That would not happen easily, because MEOH is a terrible nucleophile. So you'd have to add a bunch of heat to get that to have enough kick to knock out the chlorine. But it would still have to be SN1, because primary leaving groups are always SN1.
Oh. I was thinking like.
Oh, actually, no, I lied. This would actually have to be SN2. Sorry. It would have to be SN2, because you can't have a primary carbocation. It's too unstable. What's another sign that this would have to be SN2 and not SN1?
The internet doesn't agree with you.
What? That this is SN2?
I think it's SN1. I just Googled solvolysis, because that's a weird word.
Solvolysis is generally an SN1 reaction. You are correct. Solvolysis is nearly always an SN1 reaction. But in a case like this, if it was truly an SN1 reaction, what would happen? SN1 reaction forms a carbocation. If it was truly an SN1 reaction, this is the carbocation that would be formed. Mm-hmm. What's the problem with this carbocation?
It's sad.
Why is it sad?
Lonely. It feels incomplete. It's experiencing.
It's primary.
Depression. Oh, okay.
It's primary, and it's next to what type of carbon?
A secondary.
Secondary. So if this was truly an SN1 reaction, what's the first thing that would happen as soon as that chlorine left?
It would flip.
It would rearrange.
Yeah.
You get carbocation rearrangement, and it would rearrange to a secondary position. The fact that you do not have a rearranged product tells you that this has to be SN2. And like I said, solvolysis reactions don't happen typically in SN as SN2 reactions, because the only way you get a weak nucleophile is kicking something out. I mean, if it was secondary or tertiary, yeah, the leaving group could leave, but in a primary, the leaving group can't leave. The only way that this happens is if you add like just a boatload of heat and really speed up these methanol molecules to a ridiculous degree and wait a really long time.
Methanol don't super go together.
Yeah.
Heat and organic chemistry in general.
They go together, but it's also a hazard. Yeah. You got to be really careful. There's this terrible thing called spontaneous combustion.
There we go.
But yeah. So there you go. This is an SN2, even though it's a solvolysis. Generally speaking, solvolysis is not SN2.
Okay.
Well, I think that's probably all the time we have for this.
Another thing that I don't want to learn. Okay.
Yeah.
Great.
Yeah. Go back to that flow chart where it said SN1. Do you have a good nucleophile? No reaction. That's what it should do. Yeah.
Okay.
And so it could be one of those things where they just kind of like, oh yeah, go ahead and do this, but it's not actually something that happens.
Okay.
Cool. But anyway, there's more practice problems if you want to try them out. There's also actually, let me go ahead and let me show you something real quick. www.tccd.edu. Okay, I'm going to show something cool. Tarrant County College, go to academics.
Okay.
Labs and tutoring. And virtual learning commons online.
Okay.
That'll bring you to the learning commons page. Once here, you can go down to science support. And then lastly, scroll all the way down to online science resources under organic chemistry. Did you know about this page?
Maybe. We might have talked about it a couple of weeks ago.
Yeah, I mean, worst case scenario, I mean, you can also look at the emails that I send you. I also usually include a link to the old
yes.
Whatchamacallits. But you could click to learning workshop test review video archive. Mm-hmm. This is where I will put the recording to this session if you wanted to go back and look at it. I have a couple test reviews right now. I don't have any workshop recordings except for this one. This will be my first.
There we go.
I'm excited. But I also do have practice problems with answer keys. Now, these ones don't have answer keys because I was not allowed to give answer keys. But these ones do have answer keys, including, let's see, alcohols and alkyl halides. This is basically like the equivalent of the substitution problems.
Okay.
So there's some really cool problems in here that wants to show you. Yes, it does. Show, darn you, show. Open file. All right, there you go. Blah, blah, blah. Classify as primary, secondary, tertiary. Da, da, da. It gets down to substitution. Okay. Corresponding alkyl bromide will react more rapidly treating with hydrogen bromide. Or yeah, which of the following will react more quickly with hydrogen bromide? Okay. And it gives kind of like the comparisons between them. And the cool thing about, so that's relative rate of reactions. That's something we didn't get to. So that is actually something definitely to check out. The cool thing is the answer keys that I have for these, since I made them, I tried to make them as complete as possible. These just are naming, so I don't really do like, that much. But for the ones that like require an explanation, I explanicate it. That's not a real word.
That was good. No, that was good work there.
So, yeah. And so I kind of go through that. But it's cool. It's cool. There's an answer key. It has answers. It's pretty cool. So there's also our video tutorial library and practice test and various other cool, awesome things.
Yeah.
Including the alkyne reaction guide, and alcohol reaction guide.
Okay.
These are going to be more important in a little bit.
Cool.
But anyway, thank you so much for coming, and I hope you enjoyed it. I hope this was helpful to you.
Yeah, I appreciate it.
You're welcome. we'll see you next time.
Cool. Talk to you later, man.
All right. Bye.
Bye.